we have a couple examples. First one's going to be a uniform distribution example, and then we're going to go on and work with a bunch of examples using the normal distribution, specifically the standard normal distribution. So first we have uniform distribution. We have a packaging line at a factory, packages 200 cartons per hour, and they tracked the cartons for 1 hour and weighed them, and what they ended up with, if they charted that out, was a uniform distribution from 18.2 pounds to 20.4 pounds. And then it says an employee with a back injury is not allowed to lift packages 20 pounds or greater. And our first question is, what is the mean of the distribution? But before we even do that, let's draw it and get some values in place. So the mean is going to be in the middle. We don't know what it is yet. And then it's a uniform distribution, so it will be a rectangle. Oops. And the distribution goes from 18.2 to 20.4. So let's calculate the mean. The mean for a uniform distribution is just going to be the minimum and maximum added together and then divided by 2. So our minimum value is 18.2, our maximum is 20.4, and if we add that up we get 38.6 over 2, and divide that and we get 19.3 pounds. So we can add that to our diagram. The second question, what is the probability that a package weighs 20 pounds or greater? And a key word is probability. Probability means you're looking for an area. So on my diagram up here, I'm going to put a mark about where 20 is. It doesn't have to be perfect. I'm just going to estimate 20. And then I'm going to draw a dashed line up from 20. And we want 20 pounds or greater, so I'm going to shade the area to the right, which is greater than 20. And that's going to be our probability. That's what we're looking for. So the probability is this shaded area. So remember, probability of a rectangle is going to be the length times the height. So we need to somehow figure out the height of this rectangle. Now we know the total area is 1. So the total area is 1. And we know the total length. The total length would be the distance from 18.2 to 20.4. So I'm going to subtract those. And then we know that area is length times height. And if we want to solve and figure out what the height is, we can do area divided by length. And we know the area is 1. And now we know the length is 2.2. So our height is 0.455. So I'm going to add that to our original diagram. 0.455 for our height. Now we can use that down here for question 2. Our height is 0.455. Our length, now we're looking for just the area of the shaded spot. So we have the length of, it's going to be 20.4 minus 20 to get that distance. So we have 0.4 times 0.455, and that would come out to 0.182. So this is the area of the shaded spot in the diagram, and that is, area is always the same as probability. So that's our answer, and you can leave it as a decimal, or you could say 18.2%. Either one would be acceptable. So again, for uniform distributions, work with the total area of 1 and your total length of your distribution to find the height. Once you have the height, you can find any area that you're interested in. For the standard normal distribution, I talked in the previous video about using a table of areas and looking up your z-score to figure out an area that corresponds to that z-score. I also want you to know how to do this on your calculator, and all the examples I'm going to show in this video are going to be using the calculator to do this, and then when we're in class together we can look at how to use the table to find the area. So in your calculator, this is going to be in your distribution menu. So second vars for the distribution menu, and we're going to be using normalcdf now. So normal cumulative distribution, normalcdf. What you enter, so when you have this screen, what you enter is the minimum value in your problem, the maximum value in your problem, the mean, and the standard deviation. And let me move this out of the way so I can show you some tips. If you're looking for the area to the left of a number, so let's draw our distribution. So let's say we want the area to the left of whatever this x is. So this area that's shaded here. You would put your minimum value as minus 99. And that would ensure that it's so far off to the left that you'll include any possible little piece of area that's over here. In the second one, if you want the area to the right of a number, you go from some value of x up to positive 99. So let's say we have this x this time. And we want this area. We would go from the value of this x as the minimum out 99 to make sure we get any little piece of area that's off to the right. If you want the area between those two, and let's just change these to x1 and x2. So now let's say you want the area between them. x1 would be your minimum, x2 would be your maximum, and then you add your mean and standard deviation. And the last tip is you can leave the mean and standard deviation out if you're using z-scores. The default in the calculator is that the mean is 0 and the standard deviation is 1, which is the z-scale. So if that's the mean and standard deviation you'd be entering, you don't necessarily have to enter it. The calculator will use those values as a default. When you hit enter, the result that you get from normalcdf function is the area, which is the same as probability. Okay, so let's look at some examples. And a tip, again, is to always draw your distributions for each problem. So draw what you're looking for. So I'm going to start with these are z-scores, so z is on our standard normal distribution. We want the area to the left of z negative 1.04, which would be about right here. Now we want the area to the left. So I'll take our calculator, and we'll start from scratch here. So in our distribution menu, second vars for distributions, we want number 2, normal CDF. Now we want the minimum. Again, we're just going to plug in minus 99 because we want all the area to the left, comma. The maximum is going to be your cutoff, so minus 1.04 for a z-score. And now the mean and standard deviation is 0 and 1. I could leave that out, but if you want to just be in the habit of always using it, you can put it in, hit enter, and that's going to be our area. So 0.1492. I want you to keep 4 decimal places on your areas or probabilities. So always round that last digit. So 0.1492. And remember, that is this shaded area. So next one. We want area to the right of 2.29. So 2.29 would be somewhere out here. And we want the area to the right. Okay, so before we get too far, let's go back. Something I also want you to be in the habit of is writing down what you did to get these numbers. So let's do that for the second one, normal CDF. The values that we're going to want to put in, the minimum now is our z-score 2.29, and we're going to the right, so our maximum is going to be 99, so we make sure we get as much as possible that direction. Mean of 0 and standard deviation of 1. Oops. So distribution menu, number 2. We have 2.29 out to as far as possible, 99. 0 is our mean, 1 is our standard deviation, and there's our area, 0.0110. Alright, so last one. The area between negative 1.04 and 2.29, and we want the area between them. So same function. Our minimum now is going to be the lower z-score. Our maximum will be the higher z-score. A mean of 0 and standard deviation of 1. Distributions, normal CDF, negative 1.04, 2.29, 0, 1, and then we get 0.8398. So you'll notice that the area in the middle of these two values would be the same as 1 minus the 2 tails, which we just calculated. So the area, so the whole area is 1, If we subtract the tail that was to the left of negative 1.04, which was 0.1492, and we subtract the area to the right of 2.29, which was 0.0110, we get the area that's left in between the two. And if you were to go ahead and do that subtraction, you'd get the exact same answer as we did with the calculator using the normalcdf function between those two values. Our next example is an application of the standard normal distribution. We're going to be using a distribution that's not standard, so our mean is not 0 and our standard deviation isn't 1, but we can solve the problems using the same method. So we're going to look at the probability of different response times given a certain distribution. So we have a distribution that's normal, so let's draw a normal distribution. But now instead of a standard normal where the mean is 0, we have a mean of 8.4. And the standard deviation is 1.7. And if you were to add 1.7 on 3 times, we'd get 10.1, 11.8, and 13.5 going this way. And if we subtract 1.7 going the other way, we get 6.7, 5, and 3.3. So there's our distribution. It's a normal distribution, so we can use the z-score to standardize it and then look up the area, which is the probability, in the table, or we can use our calculator to do that. So I'm going to show you the calculation for the z-score. So we want a response time of 5 minutes or less. So let's find 5 minutes on our distribution here. There's 5 minutes. 5 minutes or less, we want the area to the left. But we can't look up 5 in the table because that's not the standard z-score. So we need to calculate the z-score first before we can look anything up. So x is going to be 5. So let's write the equation. X minus the mean divided by the standard deviation. So x is 5. That's the number we're interested in. The mean is 8.4. And the standard deviation is 1.7. We have 5 minus 8.4, and divide that by 1.7, and we get a z-score of -2. So you can see on our distribution over here, if we were to add the z distribution scale in here, 5 was right here. It was exactly 2 standard deviations below the mean. So our z-score is -2, 2 standard deviations below the mean. So that's our expected number. And then you could look up -2 in the z table, and you'd want a couple of decimals on there, so we just do -2.00, and we can look that up in the table, which I'll show you how to do during class. The other way that you can solve this problem is just simply plugging it into your calculator. We still use the normalcdf function. The small value, or the going way out to the left, again you can use -99. That's going to be far enough out there to cover everything. The number that we're stopping at is 5 because we want 5 or less. The mean is 8.4, and the standard deviation is 1.7. And again, when we plug this into our calculator and get a number back, the number is the area, or a probability. So again, distributions, number 2, and we're going from as far to the left as we can, -99, up to 5, with a mean of 8.4 and a standard deviation of 1.7. And there's our area. So 0.0228 is what we're going to round up that 7 to 0.0228. And that's it. That's the area, which is also the probability, so we're done with that one. Next one, probability of response time of 10 minutes or more. There's our distribution again. I'm not going to write the numbers again, but 10 would be just under the 10.1 that I have up on that top graph. So 10 is about right here. 10 minutes or more, we want the area to the right. Okay. Again, we could calculate a value of z. So our number of interest is 10 minus the mean of 8.4 divided by the standard deviation of 1.7, and oops, 10 minus 8.4, divide that by 1.7, and we get 0.94 for z-score. And again, you can see 10 is just under one standard deviation away from the mean, and it's 0.94. So our z-score of 0.94, we can look up area in the table. And then remember that the area that you're going to be looking up is the area to the left, and we want the area to the right. So we would do 1 minus the area that you look up in the table, and that would give you the area. And again, now we can look to see how to do it on the calculator. We're going from 10 up to as high as we can, 99, the mean of 8.4, standard deviation of 1.7. We get 0.1733. Again, that's area or probability, and that's the only number we need to answer that one. Okay. Last one of this type. We want the probability of response times between 5 and 10 minutes. So again, the mean is 8.4. 5 was here, that had a z-score of -2. 10 was right here, which had a z-score of 0.94. And we want the area between them, the response time between 5 and 10 minutes. So we have the areas of the two tails, so we could just subtract those from 1. So the whole area is 1. The tail to the left side that we're not including is 0.0228. The tail on the right side that we're not including is 0.1733. And we get 0.8039. If we hadn't already calculated those and you needed to do this in your calculator, you'd use the normal CDF function. The minimum is 5, the maximum is 10, mean of 8.4, and standard deviation of 1.7. So from 5 to 10. And we get 0.8039, same thing we just calculated. So either way you do that, you get the same answer. The last set of examples is if you know the area or the probability and you want to work backwards and find a value of z or x. There's the instructions for how to do it in the calculator, and I'll be showing you how to do that. The other way is if you're using the table in the book, you would have to scan through the whole table to find a particular probability, or at least something that's as close as possible to it. Use the z-score that corresponds to that probability, and then use that z-score to work backwards and calculate a value of x. So let's just skip right to the examples. Okay, first one, probability of 0.5832, and we want a z-score. So 0.5832 is a little over half. So I'm just going to draw a line that's a little over halfway, and remember, probabilities are always areas to the left, so this is 0.5832 is the area, and we want to know this z value right here on the axis. What you would have to do if you're using the table, again, is look through the whole table to find 0.5832, and then you'd get the z-score that corresponds to that. In your calculator, there's a function called inverse normal, and what you put in for that function is the area, mean, and standard deviation. So we're using the standard normal distribution because we're looking for a z-score. So our mean is going to be 0, and our standard deviation will be 1 in this case. And the area is 0.5832. So where we find this in the calculator is also in the distributions, so second bar is for distributions, and inverse normal is number 3. So we put in the area, 0.5832, and then if you leave the mean and standard deviation out, again it'll assume that the mean is 0 and the standard deviation is 1, but if you like to be in the habit of doing the same thing, just you put your mean and standard deviation in there, and hit enter, and we get 0.21. So our z-score is 0.21. And if you want to add that back into your axis, let's draw another one over here. On the z-scale, 0, I'm going to go out 1, 2, and 3. And 0.21 would be somewhere in here. And that makes sense. That would give us an area of over half. So our answer makes sense with the probability that was given. So number 2, we want a z-score that corresponds to a probability of 0.99. So that would be way out here. So the whole area here is 0.9900. We want to know what this value of z is that corresponds to that. And we can just plug that into the inverse normal function. So the area first, mean, and standard deviation, and we get 2.33. Remember, for z-scores we're using 2 digits after the decimal, so we're going to round that last one, so we get 2.33 for a z-score. So the next one is, again, the application. Now we're not going to have the standard distribution with the mean of 0 and a standard deviation of 1. We're going to use another normal distribution and apply what we know to that distribution. So let's, again, draw a picture. Our mean is 8.4, Each standard deviation is 1.7. So we had 10.1, 11.8, and 13.5 going this way, and 6.7, 5, and 3.3 going the other way. And we want to know what's the response time in minutes. So in minutes is going to be the same values for x down here. And we want the probability of 0.6628. Now I'm not sure exactly where 0.6628 is going to be. I'm just going to put 0.6628 and then I'm just going to draw some dashed line over here. I don't know exactly where that'll end up. But the area to the left is 0.6628. And we want whatever value of x along this scale is going to correspond to that. So in the calculator, we would put in the area, which is the probability, 0.6628, the mean, 8.4, and a standard deviation of 1.7. Distributions, inverse normal, 0.6628 for our area, 8.4 for the mean, and 1.7 for the standard deviation. And that gives us a value of x of 9.11 minutes. If you were using the table would give you a z-score. So if you looked up 0.6628 in the z-table and you got some value for z that corresponds to that, you would have to plug that into the equation. X equals the mean plus z, whatever number that would end up being, times the standard deviation of 1.7. And when you did that, you'd get approximately 9.11 minutes. And again, I'll show you how to use the table to do that kind of problem when we're all together in class. So the last one, what response time in minutes corresponds to a probability of 0.1210? Again, let's draw a picture. 0.1210 is not going to be very big. That'll be this area over here. And we want a value of x that goes with that. So this area is 0.1210. So we put in the area, the mean, standard deviation, .1210, 8.4, and 1.7. And we get value of 6.41 minutes. And that makes sense. You can see kind of where I put my x here, just as an estimate, is about where 6.4 would end up being on that scale. So again, make sure your answers make sense by drawing a picture before you start so you can check it at the end.